We're going to be looking at the equation of a line in R3. In pre-calc and calculus, you looked at the equation of a line in R2 in 2D. Here we're going to start by with this black line here, assuming this is a line in R3, and we're trying to figure out its equation. So, assuming we have an arbitrary point, call this point xyz, just point the coordinate xyz, and we're trying to figure out the equation, how to express any arbitrary xyz that lives on this line, right? To do that, we're going to begin with, first of all, drawing a pair of vectors. So let's start with a blue vector here, okay, and then a green vector. Okay. I'm going to call this point P. Call this point P. And I'm going to call this point, the green point, I'm going to call it P naught, X naught, Y naught, Z naught. Okay. So I'm going to call this vector R. R is OP. Where is O? This is O. Let me write this in blue. It's obvious why it's OP. And then R naught, I'm going to call R naught R naught is OP naught. Okay. Now, so O is the origin. So the point there is 0, 0, 0, its coordinate. So we can say that R naught, or we can see that R naught, which is OP naught, is just X naught, Y naught, Z naught, and R is just gonna be X, Y, Z. Okay? Where X, Y, and Z is an arbitrary point. Okay. Now, by the triangle rule, let's see, by the triangle rule, we can construct a triangle. So assuming we have another vector, a red vector here, let's call this red vector V. Okay? If we start from O to P naught, and then go from P naught to P, right? Then it's equivalent to going from O to P. So what I'm saying is that the green vector plus the red vector is equal to the blue vector. So what does that mean? That means that R, which is the blue vector, is equal to R naught plus V, the red vector. Okay. But we're going to do something. We're going to assume that we can push this blue vector as far as we want to push it, and bring it back as far as we want to bring. So we can go all the way here, so we get this vector here, or if we want, we can go there. So the blue vector is sliding. And in that case, if it's sliding, then it just means that we can scale the V. It just means that the length of V is changing. And in that case, we can scale it by a scalar. If T is large, then V is longer. If T is smaller, V is shorter. So T goes between negative infinity to infinity. So if v is negative, if t is negative infinity, then v is going all the way backwards. Okay. So with this, we can see that we've actually done a good job in trying to work out the equation of a line in space. So let's do a definition. The equation of a line passing through the point P0, x0, y0, z0 in the direction of the vector v. Let's say v is ABC, is given by r, but our r is xyz times x naught, y naught, z naught, so that's r naught, t, a, b, c. So this right here is equivalent to this. And then we can say that t is between negative infinity to infinity. Another way of writing it is to say that r of t as a vector is equal to x naught plus a of t, a times t, plus y naught plus bt, z naught plus ct. Or alternatively, we can say that x is equal to x naught plus at, y is equal to y naught plus bt, and z is equal to z naught plus ct. All right, so let's do an example. First example, we would like to find an equation of the line that passes through the point P0, 1, 2, 4 in the direction of v equals 5, negative 3, 1. All right. So this is quite easy. So xyz is p naught, which is r naught, which is the point here, 1, 2, 3, 1, 2, 4, plus t times 5, negative 3, 1. Or we can actually write it as 1 plus t plus 5t, and then 2 minus 3t, and 4 plus t. Okay. For t between negative infinity to infinity. All right. So that's the answer, actually. Very simple. Now let's try another problem. 3, number 2. Let's find the equation of the line segment. This is very important. From P0 is 3, negative 1, 4, to P1, 0, 5, 2. Okay. Now, we need to find a V. Our V is going to be P0, P1, which is going to be -3, 6, -2. So we're going from the line segment is P0 to P1. P0 to P1. Okay? So we're thinking that if it's a line segment, at this point, T has to be 0 and T has to be 1 here. That's the standard way of parameterizing it. We want to go from T equals 0 to T equals 1. So the equation that we want is going to be R of T is equal to, remember what we have, is equal to X naught. Our X naught is definitely going to be P0. So it's 3. And then X naught 3, Y naught -1, Z naught is 4. All right, so it's gonna be -3 plus V plus A. Our A in this case is -3, so -3t, AT plus 6t, and then minus 2t. This is one way of writing it, or you can write it as x, y, z is equal to your x naught, which is 3, -1, 4, plus t times -3, 6, -2. But the important thing here is that for a line segment, T has to go between 0 and 1. T has to be between 0 and 1. Why? Because if you check this out, assuming T is 0, if you make T 0, then this part of the equation is gone. And you just have the beginning. You just have 3, -1, 4. And if you make T1, I want you to verify that if you make T1, then you end up with P1. All right, so that's the reason why. We can talk more about it. There are other ways of explaining it, but this is just a quick way of explaining it. We can talk more about it in class. So there are two. There's an example I want you to look at, or an exercise. So I want you to try this. So A part, you want to find the equation of the line. Actually find an equation and I will explain. I want you to ask me why I used an instead of the in class. Find an equation of the line that passes through the points P0, -3, 5, 8, and P1. So when we say a line, we mean an infinite line. But when we say a line segment, we mean just a segment of the infinite line. So this is the A part, and then the B part, I want you to find the equations of the projections of the line on the XY plane. Okay. All right. So I'm gonna stop this video right here, and I will continue in the next video. The next video we're going to talk about the equation of a plane. All right.